This lecture is about how to use generative probabilistic models for text categorization. There are in general two kinds of approaches to text categorization by using machine learning. One is generative probabilistic models. The other is discriminative approaches. In this lecture, we're going to talk about the generative models. In the next lecture, we're going to talk about discriminative approaches. So the problem of text categorization is actually very similar to document clustering in that we assume that each document belongs to one category or one cluster. The main difference is that in clustering, we don't really know what are the predefined categories or what are the clusters. In fact, that's the goal of text clustering. We want to find such clusters in the data. But in the case of categorization, we are given the categories. So we kind of have predefined categories, and then based on these categories and training data, we would like to allocate a document to one of these categories, or sometimes multiple categories. But because of the similarity of the two problems, we can actually adapt the document clustering models for text categorization, or we can understand how we can use generative models to do text categorization from the perspective of clustering. And so this is a slide that we've talked about before about text clustering, where we assume there are multiple topics represented by word distributions. Each topic is one cluster. So once we estimate such a model, we faced the problem of deciding which cluster document D should belong to. And this question boils down to decide which theta I has been used to generate D. Now, suppose D has L words represented as xi here. Now, how can you compute the probability that a particular topic word distribution theta I has been used to generate this document? Well, in general, we use Bayes rule to make this inference. And you can see this prior information here that we need to consider. If a topic or cluster has a higher prior, then it's more likely that the document has been from this cluster. Right? So we should favor such a cluster. The other is the likelihood part. It's this part. And this has to do with whether the topic word distribution can explain the content of this document well. And we want to pick a topic that's high by both values. So more specifically, we just multiply them together and then choose which topic has the highest product. So more rigorously, this is what we would be doing. Right? So we're going to choose the topic that would maximize this posterior probability of the topic given the document. Again, it's posterior because this one, P of theta I, is the prior. That's our belief about which topic is more likely before we observe any document. But this conditional probability here is the posterior probability of the topic after we have observed the document D. And Bayes' rule allows us to update this probability based on the prior, and I have shown the details below here. You can see how the prior here is related to the posterior on the left-hand side, and this is related to how well this word distribution explains the document here, and the two are related in this way. So to find the topic that has the highest posterior probability here, it's equivalent to maximize this product, as we have seen also multiple times in this course. And we can then change the probability of document into a product of the probability of each word, and that's just because we've made the assumption about the independence in generating each word. Okay, so this is just something that you have seen in document clustering. And we now can see clearly how we can assign a document to a category based on the information about the word distributions for these categories and the prior on these categories. So this idea can be directly adapted to do categorization. And this is precisely what a naive Bayes classifier is doing. So here it's mostly the same information, except that we're looking at the categorization problem now. So we assume that if theta I represents category I accurately, that means the word distribution characterizes the content of documents in category I accurately, then what we can do is precisely like what we did for text clustering. Namely, we're going to assign document D to the category that has the highest probability of generating this document. In other words, we're going to maximize this posterior probability as well. And this is related to the prior and the likelihood, and as you have seen on the previous slide. And so naturally, we can then decompose this likelihood into a product, as you see here. Now here I changed the notation so that we will write down the product as a product over all the words in the vocabulary. And even though the document doesn't contain all the words, and the product is still accurately representing the product of all the words in the document because of this count here. Right? When a word doesn't occur in the document, the count would be 0. So this term will just disappear. So effectively, we'll just have the product over all the words in the document. So basically, with naive Bayes classifier, we're going to score each category for a document by this function. Now you may notice that here it involves a product of a lot of small probabilities, and this can cause an underflow problem. So one way to solve the problem is to take logarithm of this function, which doesn't change the order of these categories, but would help us preserve precision. And so this is often the function that we actually use to score each category. And then we're going to choose the category that has the highest score by this function. So this is called a naive Bayes classifier. Now the keyword Bayes is understandable because we are applying a Bayes rule here when we go from the posterior probability of the topic to a product of the likelihood and the prior. Now it's also called naive because we've made the assumption that every word in the document is generated independently. And this is indeed a naive assumption because in reality, they are not generated independently. Once you see some word, then other words will more likely occur. For example, if you have seen a word like a text, then that makes categorization or clustering more likely to appear than if you have not seen text. But this assumption allows us to simplify the problem, and it's actually quite effective for many text categorization tasks. But you should know that this kind of model doesn't have to make this assumption. We could, for example, assume that words may be dependent on each other, so that would make it a bigram language model or a trigram language model. And of course, you can even use a mixture model to model what the document looks like in each category. So in nature, they will be all using Bayes rule to do classification, but the actual generative model for documents in each category can vary. And here we just talk about a very simple case, perhaps the simplest case. So now the question is, how can we make sure each theta I actually represents category I accurately? Now in clustering, we learned this category I, or the word distributions for category I, from the data. But in our case, what can we do to make sure this theta I represents indeed category I? Well, if you think about the question, and you'll likely come up with the idea of using the training data, right? Indeed, in text categorization, we typically assume that there are training data available, and those are the documents that are known to have been generated from which category. In other words, these are the documents with known categories assigned, and of course human experts must do that. And here you see that T1 represents the set of documents that are known to have been generated from category 1, and T2 represents the documents that are known to have been generated from category 2, etc. Now, if you look at this picture, you see that the model here is really a simplified unigram language model. It's no longer a mixture model. Why? Because we already know which distribution has been used to generate which documents. There's no uncertainty here. There's no mixing of different categories here. So the estimation problem, of course, would be simplified. But in general, you can imagine what we want to do is to estimate these probabilities that I marked here. And what are the probabilities that we have to estimate in order to do categorization? Well, there are two kinds. So one is the prior, the probability of theta I, and this indicates how popular each category is, or how likely we would have observed the document in that category. The other kind is the word distributions, and we want to know what words have high probabilities for each category. So the idea then is to just use the observed training data to estimate these two probabilities. And in general, we can do this separately for different categories. That's just because these documents are known to be generated from a specific category. So once we know that, it's in some sense irrelevant what other categories we are also dealing with. So now this is a statistical estimation problem. Right? We have observed some data from some model and we want to guess the parameters of this model. We want to take our best guess of the parameters. And this is a problem that you have seen also several times in this course. Now, if you haven't thought about this problem, haven't seen naive Bayes classifier, it would be very useful for you to pause the video for a moment and to think about how to solve this problem. So let me state the problem again. So let's just think about category 1. We know there is one word distribution that has been used to generate documents. And we generate each word in the document independently. And we know that we have observed a set of n sub 1 documents in the set of T1. And these documents have been all generated from category 1, namely have been all generated using this same word distribution. Now the question is, what would be your guess or estimate of the probability of each word in this distribution? And what would be your guess of the prior probability of this category? Of course, this second probability depends on how likely you will see documents in other categories. Right? So think for a moment, how do you use all these training data, including all these documents that are known to be in these K categories, to estimate all these parameters? Now, if you spend some time to think about this, and it would help you understand the following few slides. So do spend some time to make sure that you can try to solve this problem, or do your best to solve the problem yourself. Now, if you have thought about it, and then you will realize the following intuition. First, what's the basis for estimating the prior, or the probability of each category? Well, this has to do with whether you have observed a lot of documents from that category. Intuitively, if you have seen a lot of documents in sports and very few in medical science, then your guess is that the probability of sports category is larger, or your prior on the category would be larger. And what about the basis for estimating the probability of word in each category? Well, the same, and you'll be just assuming that words that are observed frequently in the documents that are known to be generated from a category will likely have higher probability, and that's just a maximum likelihood estimate. Indeed, and that's what we could do. So to estimate the probability of each category, and to answer the question which category is most popular, then we can simply normalize the count of documents in each category. So here you see n sub I denotes the number of documents in each category. And we simply just normalize these counts to make this a probability. In other words, we make this probability proportional to the size of training data set in each category. That's the size of the set T sub I. Now, what about the word distribution? Well, we do the same. Again, this time we can do this for each category. So let's say we're considering category I or theta I. So which word has higher probability? Well, we simply count the word occurrences in the documents that are known to be generated from theta I. And then we put together all the counts of the same word in this set. And then we just normalize these counts to make this distribution of all the words, make all the probabilities of all these words sum to 1. So in this case, you can see this is proportional to the count of the word in the collection of training documents T sub I, and that's denoted by C of W and T sub I. Now, you may notice that we often write down a probability estimate in the form of being proportional to a certain number. And this is often sufficient because we have some constraints on these distributions. And so the normalizer is dictated by the constraint. So in this case, it will be useful for you to think about what are the constraints on these two kinds of probabilities. So once you figure out the answer to this question, and you will know how to normalize these counts. And so this is a good exercise to work on if it's not obvious to you. There is another issue in naive Bayes, which is smoothing. In fact, the smoothing is a general problem in all the estimate of language models. And this has to do with what would happen if you have observed a small amount of data. So smoothing is an important technique to address data sparseness. In our case, the training data set can be small. And when the data set is small, when we use maximum likelihood estimator, we often face the problem of zero probability. That means if an event is not observed, then the estimated probability would be 0. In this case, if we have not seen a word in the training documents for, let's say, category I, then our estimate would be 0 for the probability of this word in this category. And this is generally not accurate. So we have to do smoothing to make sure it's not 0 probability. The other reason for smoothing is that this is a way to bring prior knowledge. And this is also generally true for a lot of situations of smoothing. When the data set is small, we tend to rely on some prior knowledge to solve the problem. So in this case, our prior knowledge says that no word should have 0 probability. So smoothing allows us to inject this prior to make sure that no word has a 0 probability. There is also a third reason, which is sometimes not very obvious, but we'll explain that in a moment, and that is to help achieve discriminative weighting of terms. And this is also called IDF weighting, inverse document frequency weighting, that you have seen in mining word relations. So how do we do smoothing? Well, in general, we add pseudocounts to these events to make sure that no event has 0 count. So one possible way of smoothing the probability of category is to simply add a small non-negative constant delta to the count. We pretend that every category has actually some extra number of documents represented by delta. And in the denominator, we also add k multiplied by delta because we want the probability to sum to 1. So in total, we've added delta k times because we have k categories. Therefore, in the sum, we have to also add k multiplied by delta as a total pseudo counts that we add to the estimate. Now, it's interesting to think about the influence of delta. Obviously, delta is a smoothing parameter here, meaning that the larger delta is, and the more we will do smoothing, and that means we'll more rely on pseudo counts. And we might indeed ignore the actual counts if delta is set to infinity. Right? So imagine what would happen if delta approaches positive infinity. Well, we're going to say every word has infinite amount of, sorry, not every word, every category has infinite amount of documents, and then there's no distinction between them, so it becomes just a uniform. Right? What if delta is 0? Well, we just go back to the original estimate based on the observed training data to estimate the probability of each category. Now we can do the same for the word distribution, but in this case, we sometimes we find it useful to use a non-uniform pseudocounts for the word. So here you see we also add a pseudocount to each word, and that's mu multiplied by the probability of the word given by a background language model, theta sub b. Now that background model in general can be estimated by using a large collection of text, or in this case we can use the whole set of all the training data to estimate this background language model. But if we don't have to use this one, we can use larger text data that are available from somewhere else. Now, if we use such a background language model to add a pseudocount, we'll find that some words will receive more pseudocounts. So what are those words? Well, those are the common words, because they get higher probability by the background language model. So the pseudocounts added for such words will be higher. Rare words, on the other hand, will have smaller pseudocounts. Now, this addition of background model would cause a non-uniform smoothing of these word distributions. We're going to bring the probability of those common words to a higher level because of the background model. Now, this helps make the difference of the probability on such words smaller across categories, because every category has some help from the background for words like the, which have high probabilities. Therefore, it's no longer so important that each category has documents that contain such a lot of occurrences of such word, or the estimate is more influenced by the background model. And the consequence is that when we do categorization, such words tend not to influence the decision that much as words that have small probabilities from the background language model. Those words don't get some help from the background language model, so the difference would be primarily because of the differences of their occurrences in the training documents in different categories. You also see another smoothing parameter mu here, which controls the amount of smoothing, just like delta does for the other probability. Right? And you can easily understand why we add mu to the denominator, because that represents the sum of all the pseudocounts that we add for all the words. Right? So mu is also a non-negative constant, and it's empirical set to control smoothing. Now, there are some interesting special cases to think about as well. First, let's think about when mu approaches infinity, what would happen? Well, in this case, the estimate will approach to the background language model, will tend to the background language model. So we would bring every word distribution to the same background language model. And that essentially removes the difference between these categories. Obviously, we don't want to do that. The other special case is to think about the background model, and suppose we actually set it to uniform distribution. And let's say 1 over the size of the vocabulary. So each word has the same probability. Then this smoothing formula is going to be very similar to the one on the top when we add delta, because we're going to add a constant pseudocount to every word. So in general, in naive Bayes categorization, we have to do such a smoothing, and then we're going to, once we have these probabilities, then we can compute the score for each category for a document, and then choose the category with the highest score, as we discussed earlier. Now, it's useful to further understand whether the naive Bayes scoring function actually makes sense. So to understand that, and also to understand why adding a background language model will actually achieve the effect of IDF weighting and to penalize common words. Right, so suppose we have just two categories, and we're going to score based on their ratio of probability. Right, so this is, let's say, this is our scoring function for two categories. Right, so this is the score of a document for these two categories. And we're going to score based on this probability ratio. So if the ratio is large, then it means it's more likely to be in category 1. So the larger the score is, the more likely the document is in category 1. So by using Bayes' law, and we can write down this ratio as follows, and you have seen this before. Now we generally take a logarithm of this ratio and to avoid small probabilities, and this would then give us this formula in the second line. And here we see something really interesting, because this is our scoring function for deciding between the two categories. And if you look at this function, we'll see it has several parts. The first part here is actually log of prior probability ratio, and so this is the category bias. Right? It doesn't really depend on the document. It just says which category is more likely, and then we would then favor this category slightly. Right? So the second part has a sum of all the words. Right? So these are the words that are observed in the document, but in general we can consider all the words in the vocabulary. So here we're going to collect the evidence about which category is more likely. Right? So inside the sum you can see there's a product of two things. The first is the count of the word, and this count of the word serves as a feature and to represent the document. And this is what we can collect from the document. The second part is the weight of this feature. Here it's the weight on each word. Right? And this weight tells us to what extent observing this word helps contributing our decision to put this document in category 1. Remember, the higher the scoring function is, the more likely it's in category 1. Now if you look at this ratio, this weight, it's basically based on the ratio of the probability of the word from each of the two distributions. Essentially we're comparing the probability of the word from the two distributions. And if it's higher according to theta 1 than according to theta 2, then this weight would be positive. And therefore it means when we observe such a word, we'll say that it's more likely to be from category 1. And the more we observe such a word, the more likely the document will be classified as theta 1. If, on the other hand, the probability of the word from theta 1 is smaller than the probability of the word from theta 2, then you can see this weight is negative. Therefore, this is the negative evidence for supporting category 1. That means the more we observe such a word, the more likely the document is actually from theta 2. So this formula now makes a lot of sense. Right? So we're going to aggregate all the evidence from the document. We take a sum of all the words. We can call this the features that we collect from the document that would help us make the decision. And then each feature has a weight that tells us how does this feature support category 1 or does it support the category 2. And this is estimated as the log of probability ratio here in naive Bayes. And then finally we have this constant of bias here. So that formula actually is a formula that can be generalized to accommodate more features, and that's why I've introduced some other symbols here. So we introduced beta 0 to denote the bias, and fi to denote each feature, and then beta sub I to denote the weight on each feature. Now if we do this generalization, what we see is that in general we can represent the document by a feature vector f, right, fi. Here of course in this case fi is the count of a word, but in general we can put any features that we think are relevant for categorization. For example, document length, or even font size, or counts of other patterns in the document. And then our scoring function can be defined as a sum of a constant beta 0 and the sum of the feature weights over all the features. So if hf sub I is a feature value, then we multiply the value by the corresponding weight beta sub I, and we just take a sum. And this is to aggregate all the evidence that we can collect from all these features. And of course, there are parameters here. So what are the parameters? Well, these are the betas. These betas are weights. And with appropriate setting of the weights, then we can expect such a scoring function to work well to classify documents, right? Just like in the case of naive Bayes. We can clearly see naive Bayes classifier is a special case of this general classifier. Actually, this general form is very close to a classifier called a logistic regression. And this is actually one of those conditional approaches or discriminative approaches to classification. And we're going to talk more about such approaches later. But here I want you to know that there's a strong connection, a close connection between the two kinds of approaches. And this slide shows how naive Bayes classifier can be connected to logistic regression. And you can also see that in discriminative classifiers that tend to use a more general form on the bottom, we can accommodate more features to solve the problem.